Hello everyone, welcome to AI Anytime channel. In this video, we're going to look at Janus 1.3B. Okay, if you look at here on my screen, we have, I don't know, Janus, whatever you name it. It's by DeepSeek AI. It's an very novel autoregressive framework because I will tell you how they have built this a bit differently. It's an unified architecture that basically understand images and can generate images. So in general, it can handle different modalities. So for example, we call it multimodal in nowadays, right? Where you handle data of different modalities, of different dimensions. Now, we have been using models which have, a vision encoder and a text decoder and so on and so forth. Also sometimes ensemble. But here we have an unified architecture. It says a novel autoregressive. So LLMs, basically the language models are autoregressive. If you hear Jan LeCun's post or podcast, most of his interviews, he always say that LLMs are autoregressive and they are as dumb as parrot. So jokes apart. Now Janus is really novel because it says limitations of previous approaches. If you look at here, by decoupling visual encoding, so I talked about vision encoder, for example, siglip can be an example. OpenAI earlier released something called clip that we use to create features for images, right, so on and so forth. Now it decouples visual encoding into separate pathways while still utilizing a single and unified transformer architecture, which is fantastic. I mean, you have to look at novel deep learning architecture in this field right now. Otherwise, it doesn't make sense if Mistral or NVIDIA is releasing model again, one model after the other models. Doesn't make any sense to me. Those are useless, to be honest. You have to look at novel deep learning architecture, novel architecture that basically leads to something innovative, and that's what DeepSeek has done with Janus 1. Look at size, when it comes to parameter 1.3 billion, which is really is small and tiny when you compare that with other multimodal models, right? Now, this is what we're gonna use in this video. I'm already on A100 GPU on Google Colab Pro. You'll be able to run this on any other GPU as well. So simple, as I said, right, how they have performed really well on all the benchmark performance, right? You can look at MMMU and GQA and MMWeight, MMBench, so on and so forth. That's available on their GitHub repository as well. If you look at that's their GitHub repository here. It's called DeepSeek. They have talked about all the evaluation benchmark over here. Look at the result, which is really fantastic considering the parameter size are like 1.3 billion. And if you look at the sequence length also 4096, which is pretty decent. And this is good, looking at the size of the model. And you have all the code that you can of course try it out. Let's see how we can set it up here on uh, A100. Probably we can also make this available on Olama. We have to check out the compatibility, of that. So what I have done, I have git clone janus.git, basically Janus repository. You can basically you can get rid of this now. Okay, so same thing. So what I have done, you can look at here, and it says that it has been initialized. And if you come back now, what I'm gonna do is I'm gonna go cd inside it. So let me just do that. Now I'm going to cd inside Janus, and I am going into that directory. And once I go into it, let me expand that. So you can find out there is a requirements txt. So basically you have to install everything, right? Now these are built in a way where you can just use pip install -e and dot means the file inside it, which is the requirements txt, and we can just run this. Excuse me. Now, once you run this, we need to install basically flash attention because it supports, we are already on A100 and it supports flash attention too. So we're gonna use that. Whenever you install flash attention, you have to install that with no build isolation if you are in Google Colab. So let me do that. So what I'm gonna do is, and of course after this it's gonna restart the session. So let me just do flash atn, which is for flash attention, and I'm gonna say no build isolation. After that, we're gonna restart the session, guys. Don't miss to restart the session. You have to restart and again return back to the Janus folder. So it's gonna take a bit of time to install Flash Attention. You can see it says installing collected packages successfully installed. Now what we're gonna do is we're gonna restart the session. It says we're gonna lost all the variables. That is fine. We're gonna just go, we don't have any variable as of now. We're gonna just go inside cd Janus here. Excuse me, let me just go to cd Janus. You come down and you can just do present working directory to find out what's your present working directory. So let me just do that. Now what I can also do, I can just go to my gist here and I have couple of gist, you know, what I can just open it. So let me just open the gist because we're just gonna use that for inference. We don't have to write the entire code. Now, what you have to do, how you can use it, that's the question. So if you look at here, this folder called, uh, you have all the images. If you look at Janus, you have your models, you have utils, so on and so forth. You have the inference.py file as well. You have all the files, which is here. So what we're gonna do, okay, first of all, let me just import it. So I'm gonna do import torch, and once you import torch, I'm gonna do from transformers. I'm going to import auto model for causal LM. So let me just get both of it. And then we're going to use Janus.models. So Janus.models. And here we're going to import multimodality. They have, let me just do Janus.models and multi-modality causal LM. You can see it over here. And VL chat processor, which is vision language. So we're going to use VL chat processor. And from janus.utils.io, we're going to import because we're going to use some local images, so we're going to use pillow for it. So load PIL images. Oh, I have a comma here, excuse me, that's bad. Now once you run it, you are successfully able to import all the libraries that you need. So let's define the model path from Hugging Face. So what I'm going to do is model path and DeepSeek AI. Let's take it from here, guys, immediately. Then just take it from here. DeepSeek AI Janus 1.3B, and then I'm going to write VLChat underscore processor, and you can then map that with, yes, that is right, I guess. So VLChat processor, and then we have VLChat processor dot from pre-trained model dot path, and let's get the tokenizer. So what I'm going to do is I'm going to hit enter after this and say tokenizer, and tokenizer equal VL underscore chat underscore processor, and then tokenizer, and VLGPT, and then again map that with multimodalities. So vision language, multimodality, causal LM. Probably not exactly, but yeah, auto model for causal LM from pre-trained. And then you have model path. And probably we can just get rid of all of these for now. And we can just say trust remote code true. That's what we're going to do. Trust remote code true. These are not required. Okay. Trust remote code 2, and then we are going to use BF16. So let me just do that here. Now VLGPT equals VLGPT.eval, not directly eval. We're gonna first say 2, and inside this we're gonna use torch.bf16, so b float 16, that supports A100. If you are not using A100 or any latest NVIDIA architecture or Ampere architecture, you should roll back to F16, because that's the compatibility issue with flash attention and the Ampere architectures. If you don't have an Ampere architecture, it will get an error. Now CUDA here, and after that we're gonna use eval. So let me just do that. This looks good. So VL chat processor, blah blah blah, tokenizer, VL chat processor or tokenizer. and VLGPT, multimodality causal LM, auto model for causal LM, not from pre-trained. And here we have model path, trust remote code true, and VLGPT. Let's run this. Okay, let's put some images over here, or we have an image already. So let me just open this image. You can see it's an equation. So this is basically coming from a research paper, or some kind of paper, and we can just use this, whatever. So first, let's use this. So what I'm going to do is I'm going to take my Janus inference. Let's go to raw and we can explain that, of course. So what I want to do is come here and paste. So if you look at this, what I'm doing, I'm saying conversation, and then I have a list, and within list I have a lot of dictionaries with key values pairs. If you look at role, it says user. In the content, this is how you pass an image placeholder, and I'm saying convert the formula into latex code, right? And then we are passing these images, and we have equation.png over here. That's what we are passing. And we have a role as basically a system prompt kind of a guys here, thing. And then I have pillow images or PIL images, loading the PIL images conversation. Prepare the inputs. First, we have to create the features, right, of this. That's what we are doing, input and getting the input embeddings, over here. And then I'm generating the output through a language model. So if you look at it, it says vlgpt.languagemodel.generate input embeddings equal input embeddings attention mask. It an attention mask has an end of stop token, BOS, EOS token ID, so on and so forth over here. And if you come down, you can find out do sample false, use cache true, and then let me just first get rid of this here, Control C. And now let me get the print also out of here. And it says you are a helpful language and vision assistant. You are able to understand the visual content the user provides. The system prompt, then we are getting the image placeholder convert. See, here is a latex code for this. If you look at the assistant answer, of course, you can parse that as well. If you look at here, it says here is the latex code for the formula. And if you look at the formula, it says an blah blah blah. This basically gives you the formula. I want to try it out with some my like if I have some images, so I'm going to upload some images over here. So I have a car image. So let me just upload that car image over here. You can see I've uploaded a car.jpg. So I'm just going to come and just run this again. I want to try it on a bit complex images. Let me just do that. And it's pretty fast, guys, on A100. Like, when it comes to inference, like takes few seconds, like around 3 to 5 seconds to generate an answer. If you look at here, it says, oh, actually, I forgot to change this. Can you generate the insights from the image? So let's see if it's able to generate. And let me show you the image, by the way. So this is the image. You can see like two cars have been collided or something, So let me just generate. This is very helpful in insurance use cases, guys. In insurance industry, where you want to run some digital forensics on crash sites. If you look at it, says the image is seen of a car accident on a city street, so which is right. It says the two vehicles involved in the collision are a red sedan and a blue minivan. Ah, all right, okay. The red sedan is on the left-hand side of the image, showing significant damage, which is fantastic, right? This will help the insurance industry, guys. Of course, you have to scale this use case, but you can build some touchless claims kind of a thing using these models right now. That's the one thing. Let's upload some other images as well. So I have probably, if I go to my screenshots, I will have an image here. Let me just upload an image, and of course I'm going to rename this. So let me rename this to NVIDIA, which because it's an image of like a stock, like it's a chart. Okay, it's a chart that I've got it from Yahoo Finance, for NVIDIA. So I'm just going to do NVIDIA PNG. Okay, and can you explain the chart to me? Let me do like this. Okay, and we'll see. how it responds. It's able to understand, like, the first use case where, you want to build some claim adjustment kind of a tool, completely digital, of course, using OCR and these kind of technologies, like bringing up multimodal generative AI. I think, of course, you can do that. If you look at here, it says the chart has the following element. The image is a financial chart, which is fantastic. I really liked it, guys, over here. So let me just take a screenshot of this over here. I really liked it. Yeah, this is good. Okay, we can. This is nice. Okay. Uh, I'll take one more screenshot till here. Okay. Now you can see it says x-axis, y-axis. Let me show you the image, then you'll understand better. This is an image. Uh, and if you look at here, it says x-axis date, y-axis percentage change, data representations, stock performance over time. You can see it over here. Color coding, it gives you key observation. The stack shows significant volatility with sharp peaks and troughs. These are periods where the stock's values increase followed by a sharp declines, blah, blah, blah. Right? Now, this is good. What we're gonna do next, guys, is try to understand how we can generate images. As I said, it understand and it also generate images, two in one. So you can build some rack kind of a pipeline with this and Colpally, for example. I have a video on that, or you can use Olama. We have to first make sure that this model is compatible and available through Olama. Look at how we can generate an image over here. So what I'm gonna do, I'm gonna say image generation. Now in image generation, I have, of course, let's get import OS, and I'm gonna have pil.image, and then I have import torch, and then I have import numpy as np, and I have already transform multimodal. And let's just run this. Now what we're gonna do next is we're gonna we already have the models and everything, so we're not gonna do load the model again. We are basically going to just generate. So it's not a lot of difference when it comes to this. I'll show you. Okay, let me just copy this. Okay, now the major difference that we have here, if you look at, so let me just do one thing, come over here. Okay, so we're going to create a content. So let me just say generate an image of a of a of a lion in a dense forest or something like that. Okay, now if you look at the conversation, earlier we have on, if you go on here, earlier we had content image placeholder, right? This part. If you look at this part, we are not going to do this here. Okay, we are not doing that. Okay, so let me just come a bit down. Here we have the same thing in the conversation except image placeholder, not passing the placeholder. And now we have SFT format over here. If you look at this SFT format, it applies SFT template for like multi-turn prompting. You should watch my previous. I'll give the link in description where I've explained these terminologies. What does this terminology mean, right? And then we create a prompt with SFT format plus VL chat processor, that we have. Now here we have a generate using a decorator that's called torch.inference mode, and then we are using generate. We have a couple of params over here, like the temperature value, the CFG weight, which is used in diffusion models, image token number per image, blah blah blah, right? And then we get the IDs of all this after tokenizing it, and then we get the embeddings using this line if you look at here, and then we generate the token, and then we of course decode it. Right? That's what we are doing here. A bunch of other things that you can see the same thing which have been used previously in calculating. If you look at it, it says np.clip. Okay, pretty much standard thing, guys. Here over here, if you look at it, it says this is the resolution of it, and the RGBA, whatever images that you are looking at, and it's using clip, numpy.clip. Okay, and then basically generate the sample. Basically creates a directory for you. Okay, it creates a directory, and then you can just generate over here. So it has the ability to generate as well, this thing, and which is fantastic. If you want to understand a bit more about the code, I recommend you read the research paper, where uh, they cover this in detail on about each terminology that you see. Uh, what does each line means. For example, what is SFT format, how does this prompt is working, what is this function is doing, so on and so forth, right? If I can also explain that in a bit detailed, yeah, we can do that, but that will take time, right? This, if you talk about this function, is basically used for efficient inference. That basically disables your something called gradient computation. And this is like a function that takes, as I said, various parameter. This is model used for generation. If you look at this one, this is a processor for handling visual and language tasks. This is a formatted prompt string. These are all hyperparameter, or most of it like are inference parameters when it comes to this function. Now, if you come down here, let me explain that. I don't have my tab with it, otherwise I would have explained in a bit intuitive way. Now, here we are doing the tokenization, guys. The prompt is tokenized into IDs suitable for the model, because the model understand features, right? Numerical representation, and a token arrays, over here, token arrays. Now, a tensor of zeros, over if you look at this, a tensor of if you look at tensor of zeros is created to hold the tokens for multiple parallel generations. So for odd indices, padding tokens are added over here. If you understand this piece of code over here. Now, in the input embeds, if you look at this pad ID, right, this basically adds, like just pad tokens are added, for odd indices. Okay, over here, if you look at this, if I, not 2, and then that's what we are doing over here, right? Now, if you look at this, it's an input embedding. So the tokens are converted into embeddings, as I said, which are numerical representation the model can process. And this goes into a for loop over here. It's a generation loop for a predefined, number of tokens, like whatever image parts that has been given, to it. The model predicts the next token based on the input embeddings, and of course, conditional and unconditional logits. If you look at these logits conditions and logits unconditionals are computed over in these two lines over here, and a new token is sampled, you know, uh, from the probabilities and is stored over here. If you look at this part, okay, these generated tokens, that's what it has been done. Now, once you do that, you have to save that. So you have to do the decoding of it. So if you look at DEC, which is an acronym for decoding, you know, and decoding and saving the images, right? Now, the generated tokens are basically converted back into an image format because we are generating an image, right? And we are processing the image, are normalized and reshaped over here. That's what I said, normalized and reshaped, and then save the image into this directory over here. That's what we have been doing, right? Now, these are function calls, guys, generate. Let's see if this works. I haven't tried it yet, to be honest. Let me see that. See how much time it takes. Okay, so I don't know, it's like there's something it's not saving, so that's why it's showing it here. Yeah, but so this entire code that you see, basically it combines basically natural language, guys, with image generations and creating images based on the user defined prompt, so on and so forth. That's what it does. Now, if you if you look at here, right, uh, our code has been ran successfully, and now we have to go to Janus. So let me just go to Janus, and in the generated samples folder you can find out the images. Oh, okay. This is a lion. There is a lion. Oh, all right. All right, I like this one. Let me just save this guy here. Okay, uh okay, let me just save this. Okay, this is not good. So all of these are of course not of good quality, to be honest. Okay, and I don't expect all of to be good quality, to be honest. Some of it will be good quality, of course. Some of it will not be good quality, but yeah, fantastic looking at uh, the size of the model. To be honest, the clarities are there. By the way, the the intricate details that it has followed is there. I really liked it, to be honest. Yeah, let me just get rid of this. I have opened multiple images, might hang guys a bit. Yeah, but I hope you got a bit of idea how to use Janus, for both image understanding and image generation as well. A single model that can do both. You can generate images, you can, of course, understand images. So understand and generate different modalities. You can, of course, we'll try to use this for our RAG pipelines. We'll see how we can use this with Colpulli. I have already have a video on Colpulli with QNVL, the QN models. I will recommend you to watch that video. But this will be available on my GitHub repository. I'll also give links of other multimodals video that you may like it. Okay, so if you like this content, please hit the like icon. And if you haven't subscribed the channel yet, please do subscribe the channel, guys. That motivates me to create more such videos. Okay. If you want to join our Discord community, please join it. I'll give the link in description. Okay, if you haven't subscribed the channel yet, please do subscribe the channel again, I said, and you can share the video with your friends and to peer. Thank you so much for watching. See you in the next one.